We start with some function of x, draw it on a graph, and ask the question, what is the area between this curve and the x-axis between two fixed points? This seems an impossible task to get an exact answer. The only time we are able to find the exact area of a shape is when that shape is nice and regular, like a rectangle or a triangle, or when it is made up from a combination of these regular shapes, whose areas can be calculated individually and then summed up. We are going to try to break our area into a combination of regular shapes, rectangles. The height of one of these rectangles that starts at position x is the height of the curve at that point, and the width of the rectangle we call delta x. Clearly, with this small number of large, bulky rectangles, the total combined area of the rectangles does not equal the area under the curve, but it is an approximation. How do we improve this estimate? Well, we do so by increasing the number of rectangles and thereby decreasing their width. The exact area under the curve is found by adding up the areas of all the rectangles in the limit of infinite rectangles, with each of them having an infinitesimal width. This limit of summing together an infinite number of infinitesimally small chunks is what defines a definite integral, and it corresponds to the area under a curve because each of these small chunks corresponds to a small bit of area under the curve. Switching to a more real-world picture, let's look at the familiar formula distance is equal to speed multiplied by time. We have used this many times before in problems where an object is moving with a nice constant speed. But what about if this speed is changing over time? How can we calculate the total distance travelled between two times in this case? We again try to break it up into infinitesimal distances travelled in infinitesimal times and add these all together. At a certain time, the object has a certain speed, and so as time changes by a tiny bit dt, the object moves a tiny distance given by its speed at that time multiplied by the amount of time that has passed dt. The distance moved in the next infinitesimal time block is given by the speed at the new time multiplied by dt. Adding all these segments up means doing the following integral, and it should come as no surprise that we are finding the area underneath the speed-time graph. This concept can be extended easily, and I encourage you to think about other formulas this method would apply to. Now we need to calculate these definite integrals, the infinite sums with upper and lower limits. Let's use this example. We must first ignore the limits and ask, what does this function integrate to? We need to find the function which, when differentiated, leaves us with this. In this case, we get the following function. Notice that because we are doing a definite integral, we don't need a plus c, and we will see why in a second. Now for the twist. To find the result of this definite integral, which tells us the area underneath the corresponding curve, we must evaluate the integrated function at the upper and lower limits. And we must find the difference between these two results. This means subbing in the upper limit, getting a number, subbing in the lower limit, getting a number, and taking away the second number from the first. This subtraction step explains why we don't need to worry about the plus c, since it would cancel out anyway.